Previously, we discussed how to calculate the entropy for systems that involve multiple energy levels. What we'll do now is we'll talk about how to define the equilibrium behavior of these types of systems. In order to identify the equilibrium behavior, what we want to do is we essentially want to find the conditions that minimize the Helmholtz energy of the system. And so we're going to be looking at a system in which the volume and the number of molecules is going to be held constant. Now, by definition, we know that the Helmholtz energy is just the internal energy minus T times the molar entropy. If we write the Helmholtz equation in differential form, we'll have something that looks like this. Okay? And we know that if we want to minimize the Helmholtz energy, that this total differential needs to be equal to 0. All right? And so if we want to minimize this Helmholtz energy or find the conditions that minimize the Helmholtz energy, we need to figure out how to describe the du and the ds for systems that have discrete energy levels. To describe ds, we could use the entropy equation that we derived earlier. Specifically, we could use a Shannon entropy formula. And so here, the molar entropy is going to be equal to negative Kb times the summation from I equals 1 to T categories, or T energy levels, the probability of a certain energy level times the natural log pi. Right? That's from the previous video. Okay, and so that's what molar entropy is. What we want is the total derivative of that. So we're just going to take the derivative of the molar entropy with respect to the probability. Okay, so here we'll get Kb times, and then we have to employ the product rule. dpi plus, and then pi times the derivative of ln pi, which we'll just put a pi in the bottom here. So this is another dpi. Okay. All right, so these pi's cancel, and we get 1 here. All right. And so what we get for ds is just going to be negative Kb times 1 plus ln of pi dpi. Okay. All right, so that's how we get the ds term in the Helmholtz differential. What we need now is to figure out how to get du. Now, to calculate the internal energy, we're going to make an assumption. In the previous video, when we described the different energy levels, we referred to those different energy levels as epsilon sub I. Right? So epsilon 1 would be the energy level of the ground state, epsilon 2 was the first excited state, and epsilon t was the highest excited state. And so what we're going to do is we're going to assume that the internal energy of a system is going to be equal to the average epsilon sub I value. Assume that it is equal to the average epsilon sub I value. Okay? And so that would mean that our u is equal to the average of epsilon. And so in order to calculate the average, we'll just use our definition, mathematical definition of the average, which is epsilon, the summation of epsilon sub I times its probability. Right? We're just using the regular average formula. So that's what u is going to be equal to. So if we take the differential of that, we're going to take the differential of this right-hand side. So we'll keep the summation. And so once again, we'll employ the product rule. Okay. All right. So here we'll take the derivative of p first, And then on the second term, we'll take the derivative of epsilon. Okay. All right. And we know that for this d epsilon sub I, that it will actually cancel out. Because this epsilon sub I, the actual energy level itself, is just a function of V and N. Let me make this 0 bigger. So this term is going to be 0. Because the number of, or the actual energy of a particular energy level, that's just a function of the volume and the number of molecules in the system. Right? It's not a function of temperature. Right? The distribution is a function of temperature, but the energy level itself is not a function of temperature. All right, so really, epsilon's only a function of V and N. And in this problem, we're keeping V and N constant. All right, so because we're keeping those constant, the second term is going to go away. And so for du, what we're going to be left with is just the summation of epsilon sub I dpi. So now we have both ds and du. So for our Helmholtz dA, we can now just plug in. So we'll plug in du, epsilon dpi, and then we're going to plug in our ds. Here we have a negative, and our ds also has a negative, and so as a result, those negatives cancel, and we get T kb 1 plus ln pi dpi. And if we're trying to find the minimum, we know that this dA is going to be equal to 0. All right, so this is the sort of relationship that describes the minimum of the Helmholtz free energy. But this isn't the only sort of equation we need to consider. Because what we have to remember is we're dealing with probabilities. So since we are dealing with probabilities, what we know is that we actually have a constraint we need to obey. Specifically, we know that the sum of the probabilities has to be equal to 1. So we have this constraint, and our constraint is that I'll call a function g, which is going to be a function of the probabilities. Our constraint is that the sum of the probabilities is equal to 1. All right? Okay, so we have this constraint, and what we want to do is we want to minimize this Helmholtz function. So just to summarize, our goal is we need to minimize our a function, and our a function itself is subject to a constraint g, which is a function of the probabilities. Okay? All right, we have this function that we want to minimize, and we have to obey this constraint. Hopefully, this sort of premise rings a bell, because in order to solve this problem, if you remember from Module 1, the mathematical technique that is appropriate for solving this problem is to use a Lagrange multiplier. To do this. Okay? All right, and so essentially, for the Lagrange multiplier, what we're going to do is we have to just write an equation in this format. Where this lambda, that was the Lagrange multiplier. Right? That's the sort of constant that we need to figure out. Okay? All right, so this is the Lagrange multiplier we need to calculate. And so we'll just plug in for dA and dG. For dA, we already have that equation. We'll plug it in. So the summation I goes to 1 to t of epsilon I dpi plus kBt times 1 plus ln of pi dpi. All right, and then now we have our lambda. And now we need to take the derivative of dg. Fortunately, the only thing in the g function is p, so its derivative is fairly simple. Just dpi. And all of that is equal to 0. Okay? All right. Now, all of the terms in our Lagrange multiplier have the derivative of the probability. So what we could do is we could factor that out. And we could just write all of this in brackets. 1 plus natural log of pi minus lambda dpi equals 0. All right, so in our Lagrange multiplier, we have this sort of statement. And if you remember from our previous lesson on Lagrange multipliers, in this sort of bracket, in order to satisfy the minimization calculation, when we have the sum, essentially what we need is for all of, or each I value, everything in the brackets needs to be equal to 0. Must equal 0 for each I. Okay. All right, and so if we know that everything inside the brackets needs to be equal to 0, we could just write this additional equation, or just write the Lagrange multiplier equation like this. kBt 1 plus ln of pi minus lambda, that's equal to 0. Okay. In the end, what we want is the probability. And so if we resolve this equation, we get that pi is equal to the exponential epsilon I over kBt plus lambda over kBt minus 1. Okay? All right, so we have this probability equation, and I'll talk about what we could use it for in a bit. But we still do have something we need to take care of, is we need to figure out what the actual Lagrange multiplier constant is, this lambda. All right? And so in order to calculate it, we're going to follow the same strategy we used before. And at this point, what we're going to do is we're going to apply our constraint. So to get rid of lambda, we'll apply our g constraint. And so that constraint is that the summation of our probabilities is equal to 1. Okay? All right, so this is what our summation is equal to. But we also have a functional form for that probability now. So the summation of the exponential of, oh, I think previously, if I take a look at this, there should be a negative here. So, because to solve for p of I, you need to move this to the other side. Okay. In any case, so in our equation here, we're going to have negative epsilon I kBt plus lambda over kBt minus 1. Because we're dealing with exponentials, we could play around with our exponential rules, and what I'll do is I'm actually going to factor out this term. I equals 1 t, so we get exponential of negative epsilon I kBt, and that's going to be times the exponential of lambda kBt minus 1. Okay? Alright, so I have this sort of equation. Alright, and we know that this constraint, which just tells us summation of the probabilities, which is equal to 1, is equal to this term. Okay, so I'm going to call this equation 1. Alright, and so if I rewrite the probability, what I'm going to do is I'm going to play a trick that involves this equation 1. Okay? And essentially what I'm going to do is I'm going to divide the probability by 1. Okay? And what I mean by that is, we have our probability here. I'm just going to divide it by the number 1. Right? So that shouldn't affect the value. So that's still pi. Alright, and we know the probability is the exponential, and I'll write it in the factored out form. The exponential times this. Okay? So that's what the probability is. But what we're doing is we're going to divide the probability by 1. And we know, based on equation 1, that 1 is also equal to this summation. So we'll plug that in. Okay, all right. And so we have this statement, and furthermore, this term right here, it's not a function of the I index at all. So we could actually take it out of the summation. And when we do that, we're going to have it both on the bottom and the top. So as a result, the term with the Lagrange multiplier constant actually just ends up canceling out. All right, and so what we find is that the probability, right, that a particle ends up in a specific energy level, we can actually just describe it using this fairly simple equation. Okay. All right. And so this equation, it's simple but very powerful. Right? In fact, because it's so powerful, it has a name. It's known as the Boltzmann distribution law. And what it tells us is that the probability that a particle is in a particular energy level can just be described by this ratio of the exponential of the energy level divided by the summation of all of the possible energy levels. Right? And so to get a handle to make this illustrate this probability distribution more concretely, we can actually just take a look of it plotted here. All right? And so what you're looking at here, the y-axis is the probability as a function of the internal energy, and the x-axis is the energy level. Right? So really, you could think of this as your epsilon I. All right, and so when epsilon I is low, right, that's our lowest energy level, and we find that if we just stick to this curve, at lower energy levels, we find that the probability that a particle is in those lower energy levels is higher. And as we increase the energy level, then that probability decreases monotonically, right? There's like an exponential decay. And so that part's general. But what's interesting here is in the equation, not only do we see the dependence on the energy level, we also see the dependence based on temperature as well. And so according to this Boltzmann distribution law, if we increase the temperature of the system, it's going to flatten out the distribution. So now, rather than just having a high probability at low energy levels, instead, we're going to see that the probability that a particle is in, the various energy levels, that distribution is much flatter, right? And so it means there's a higher probability it's in these higher energy levels, all right? And so that's the sort of power of the Boltzmann distribution law, right? We're taking a very simple system where we're dealing with particles that can exist in discrete places. We could describe the probability distribution of these particles. All right? Now, with the Boltzmann distribution law, I kind of want to break it down a little further. So in the numerator, we have this exponential term, right? And so in the numerator, we could describe, or what you'll typically see in the literature, is that anytime you have a probability distribution that's based on an exponential with some sort of energy in it, that's going to be known as a Boltzmann factor. Okay? So that's just what this is. And so this Boltzmann factor, the physical sort of meaning of it, is it just specifies how particles are partitioned in accessible states. Right? So, for a given energy level, when you plug it in here, this exponential of that will kind of give you an idea of the magnet, or how many. It's proportional to how many particles are in that energy level, right? Now, the denominator here, we have the summation. This denominator has a very special name, okay? So it's going to be known as the individual particle partition function. And we typically abbreviate it as lowercase q. So lowercase q is just the summation of our different Boltzmann factors. Okay? Or we could write it like this. Okay? And so essentially the partition function, just mathematically, it's a sum of the Boltzmann factors. And moving forward, when we talk about probability, we're typically going to write it as a Boltzmann factor divided by the partition function. And so the way to think about the partition function, we could tie it back to our discussion about probability all the way back in Module 1. Such that the partition function, really, one of its main purposes is that it just normalizes the distribution function. Normalizes probabilities so that when we add the probabilities together, their sum is going to be equal to 1. Okay? All right, and so here, I want to introduce, by trying to find the equilibrium sort of probability distribution of particles throughout the different energy levels, we have a description for it And the function that describes p sub I is going to depend on this kind of newly defined partition function.